Thanks, Jules. Good morning, everyone. My name is Samir, and today I'm going to talk about performance of Spark's execution engine. More specifically, this talk will focus on the project Tungsten, which has been responsible for improving the Spark's performance by almost an order of magnitude over the period of the last few months. So just a brief introduction about me. I am a software engineer at Databricks, where I work on Spark Core and Spark SQL. I recently finished my PhD in databases from UC Berkeley AMP Lab, where my research focused on BlinkDB, which is an approximate query processing framework that's built on Spark. So let me motivate this talk by highlighting some of the recent hardware trends and how they have changed over the last few years. So right around 2010, back when the Spark project was started, if we look at disk bandwidths, they were almost of the order of 50 megabytes per second. Network bandwidths were around 1 gigabit per second. And CPU was around 3 gigahertz. Fast forward to today, now we see that disk bandwidths are of the order of 500 megabytes per second. SSDs-like environment are not very uncommon in data center-like environments. SSDs are not very uncommon in data center-like environments. Network bandwidths are of the order of 10 gigabits per second, whereas CPUs have just about remained the same. So while we see almost an order of magnitude more improvement for both storage and network, we see that CPUs, on the other hand, have just about improved by 20 to 30% in the best case. So this change in hardware landscape actually made us revisit some of the core performance characteristics of Spark to make sure that we can actually take advantage of these changing trends. Now, that was the hardware side of the story. What about the software side? So if we look at the Spark software stack, Spark in itself is traditionally optimized for I/O. First of all, we aggressively reduce the amount of data a query reads by pruning on the unnecessary data in case the query does not need it. Second, as part of setting the 2014 sort record, we essentially rewrote major parts of the shuffle and the network implementation layer such that it's much more modern and performant. If we look at the Hadoop ecosystem as a whole, there has been a wide variety of changes to improve data format density. What this means is that if your data is in a dense format like Parquet or ORC, there is inherently a less need to read data. For example, if I have a 1 gigabyte Parquet file or an ORC file, that can in turn hold a larger number of rows compared to a 1 gigabyte CSV or a JSON data. So we have two trends. On the hardware side, we see that the disk and network bandwidths have gone up by almost an order of magnitude. And on the software side, we see that, again, I/O has been the focus of a lot of performance improvements over the years, both in Spark and the Hadoop ecosystem as a whole. So this has actually resulted in an increasingly new trend where the CPU now becomes the new bottleneck. And we do expect this trend to continue for the next few years. So with this trend in mind, the goal of Project Tungsten is to substantially improve the memory and CPU efficiency of the Spark backend execution engine and to push the performance closer to the limits of modern hardware. So if you look at the Spark stack, the Tungsten execution engine lies right at the bottom of the stack. Any query that we write in SQL, Python, R, or streaming essentially gets converted into a logical plan, which then gets executed on physical machines using the Tungsten execution engine. Just one thing to clarify here before I go into the rest of the talk. The focus of this talk would actually be on the execution and not the optimizer. Why do I make such clarification? The reason is that it's relatively easy to basically optimize your query and, let's say, pick a better broadcast join implementation, which is way more faster than, let's say, the Cartesian join for a certain kind of query. But it's significantly much harder to take in an operator and to optimize it and even make it like 10 to 100 times faster. And the latter would be what I'll be focusing in this talk. So in the previous few releases, we laid the foundation of Project Tungsten Phase 1 by improving the memory management. We built the foundation for support of runtime code generation. And then we implemented a number of cache-aware algorithms that could take advantage of these changing hardware trends. Now, in Phase 2, we actually set out with an ambitious goal that was part of Spark 2.0 release, and we wanted to really make Spark's execution engine almost an order of magnitude faster. And in this, I'll be mostly focusing on two key techniques that has been responsible for doing that. One is whole state code generation, and the second is vectorization. So just a brief summary of what was part of phase 1 before I actually go into phase 2. So there were really three things that we looked at as part of Project Tungsten phase 1. First, we did explicit memory management instead of relying on Java objects. And what this means is that by this, we were able to reduce memory footprint by almost eliminating garbage collection overheads. And we did this using the Java unsafe rows and off-heap memory. Second, we worked on code generation for expression evaluation. I'll be talking a bit more into this, like in the rest of my talk. But this enabled us to reduce many virtual function calls and interpretation overhead. Finally, we also worked on a number of cache-conscious sorted algorithms that could identify and reduce many of these bad memory access patterns and can take advantage of these changing hardware trends. So this was great, but how do we make Spark 10 times faster than it was today, or maybe at 1.6? So one thing to notice here is that for performance improvements as dramatic as we are aiming for, many of the traditional profiling techniques don't really work so well. Now, what do I mean by a traditional profiling technique? By a traditional profiling technique, we mean something like taking Spark, taking a profiler, running the profiler on Spark, and trying to identify pieces of code that might be just inefficient or badly implemented, and just trying to maybe rewrite them and make them more performant. However, if we take a step back and think about it, in order to make a system 10 times faster, we really have to find about 90% of this so-called hotspots that would make up for 90% of the query execution time, and then magically make them instantaneous. Similarly, in order to make something 100 times faster, we really have to find out 99% of these hotspots and then magically make them instantaneous. Now, this is not really practical for a profiler. The profilers more practically can shave off maybe like 20, 30% of your query runtime in the best case, but they will not be able to achieve around 10 to 100 times improvement for any code that you have. That said, we have seen in the past systems that can actually give 10 to 100 times improvements over traditional systems. For example, not too long ago, Spark, when compared to the initial version of MapReduce, was almost 100 times faster. So instead of actually trying to see how well we can run the existing Spark code, we instead tried to look at this problem bottom up. We tried to ask this question of how fast should a query run, and not how fast can we make a certain code run. So let me illustrate this with a very simple example. Let's say we have a simple query. It basically does a select count star from a table and filters across an attribute which is equal to 1,000. Now, on the right side, I have the physical plan for this query. Right at the bottom, I have the scan operator that basically scans the store sales table. The filter operator looks for this attribute or this column, SS item SK, and looks for the values of 1,000 and then prunes it. The project operator prunes out all unnecessary columns just because this query does not need evaluating them. And finally, the aggregate operator just returns the count. Now, to evaluate these kind of queries, Spark, and more generally, like any database system that we have, essentially relied on this Volcano iterator model. This technique has been a standard in database literature for almost the last 30 years or so, and it is basically behind many large distributed parallel databases that we have or use today. Now, what is this technique? In the Volcano iterator model, each operator is implemented as each operator exposes an iterator interface that essentially consumes the operator from the operator below it, or the child operator, processes that operator according to some logic, and then optionally exposes or releases that record to the operator that's above it. So as an example, if you look at the right, we have the code for the filter operator as implemented in the Volcano iterator model. You have the next function that this operator interface exposes. It in turn calls child.next. You can see some code that has logic for evaluating the predicate in this filter. And then it optionally returns the row or the record to the operator that's above it. Now, there are two key advantages of the Volcano iterator model. First of all, it's really simple to reason about when you are adding new functionality in the database. All every operator has to do is to expose an interface that has some logic of processing the rows it gets, and it basically has to have some logic of releasing these rows to the operator that's above it. Second, and more importantly, this interface actually allows, or this model actually allows these operators to be very composable. When you're writing a filter operator, you don't have to really worry about the fact that this filter is followed by a scan, or maybe this filter is followed by a project or another filter. All you have to worry about is exposing this simple iterator interface, and then all these operators can be composed together. The downside of this model is that it's not the most CPU-efficient way to execute a query. Now let's hold on to that thought and actually do a slightly different exercise. Let's ask this question. What if we actually hired a college freshman to implement this query in Java in 10 minutes? So we have the same query. It selects a count star from this table, and it filters across a certain attribute. Now the answer here is fairly straightforward. If we give a college freshman 10 minutes, here is something she would come up with. You essentially have a loop that scans over this entire table. You have an if condition that probably just filters that column and then increments a count. Now, one thing to notice here is that this code, this 4 lines of code, is already way more simpler than just the filter operator I showed you. And the filter operator was not even implementing the entire query, whereas this does. The other thing is that this code is actually pretty much a one-to-one mapping between the SQL code and the corresponding Java code. Let's reason about performance. What do you think would be faster? Would it be the code that's written in the Volcano model that's essentially backed up by 30 years of database research, or would it be something that a college freshman came up in just 10 minutes? So we ran some benchmarks, and we found that the Volcano iterator model, in this case, was able to process around 14 million rows per second. So this was a simple query. It was just running an L2N benchmark on Parquet data, single column, and it was just trying to execute that query. So 14 million records per second was the throughput or the processing rate for the Volcano iterator model. The college freshman, on the other hand, the simple code was able to process close to 125 million records per second. So there is something really interesting that's going on here. And then we wanted to investigate what's really going on. So how does a student actually beat 30 years of database research? The Volcano model, as I presented it, had a number of shortcomings. First, it had a lot of virtual function calls. So since you're agnostic to the operator that's below you, and you don't know where the row is actually coming from, at runtime, it's all dynamic dispatching. Second, there is a standard row format that's actually being passed between one operator to the next operator. And that actually means writes to the main memory, or it might be L1, L2, L3 cache. Now, what this means is that if I have a chain of these operators, every operator has to write its intermediate data, or the row, to memory, or the cache, and the next operator has to read it. Now, if I'm talking about processing millions or billions of rows, this intermediate data, or the memory access, quickly becomes a bottleneck. Third, this code, or this style of code, the iterator model, is generally very confusing for the compiler to understand. What this means is that it cannot take advantage of many of the modern CPU features, especially things that a lot of architecture chips have been improving over the years. For example, it's difficult to figure out and do like loop unrolling, SIMD, pipelining, prefetching, branch prediction, and so on and so forth. The handwritten code, on the other hand, did exactly the opposite things. It had no virtual function calls. The data was always in the CPU register, so it was the count variable. This style of code was very simple. So it was able to leverage, the compiler was able to leverage all of these traditional optimization techniques, such as loop unrolling, SIMD pipelining, and things like that. So in all, the handwritten code, the 4 lines of code that we had, was able to take advantage of all the information that was actually available after query compilation. It was actually just designed to run that particular query that you were trying to write and not do anything else. The Volcano iterator model, on the other hand, paid a cost of generality. It was able to expose a general interface. It was able to basically support a wide range of queries. And it turned out that it was very hard for that code to execute on machines. So this was the key insight or the idea behind whole state code generation. The idea behind this technique is that we actually fuse operators together. So the set of 4 operators that we saw, scan, filter, project, and aggregate, we fuse these together such that the generated code looks very close to the handwritten code that I showed you. We do this using 3 things. First of all, we identify chains of operators or these stages that can actually be fused, and there are certain rules for doing that. Second, we compile each of these stages into a single function. So in that case, in the previous example I showed you, it would have been something like a for loop with an if statement and a count. And finally, the goal here is to actually get the functionality of a general purpose execution engine. We would not want to write these fusing rules for like some hand-tuned query or a specific subset of queries. We would like to support a general set of queries. But simultaneously, we would like to actually get the performance as if somebody just hand-built a system to run your query. So this is just another example of how whole-state code generation works. This is a slightly more complex query. It has a join in it, along with like filter, projects, and aggregates. Now, this actually might be a familiar site for many of you. This is, if you go to the Spark SQL page or Spark UI page and click on the SQL tab, this is one of the query plans that basically looks like. And if we have query plans like this, the whole-state code generation essentially, first of all, identify pipelines that can be fused into a single function or compiled in a single function. And as I said, there are like various rules that you can have so that you can break your query into like these pipelines. And then for each of these pipelines, we essentially look at the stages or look at the operators that are part of this pipeline, and then try to generate code that essentially maps from these operators. So in this particular case, we would get something like this. The scan operator below would produce something that's equivalent to the for loop that we have here. The filter operator here would have just some kind of like a filter function or an if condition, and the aggregate operator would have just a counter increment. So essentially, there are, as I said, various rules of how you can break a general query into various pipelines. And within each pipeline, how can we actually map these operators into various hand-generated code? So there is a great paper by Thomas Newman that highlighted a lot of these interesting ideas that was published in VLDB 2011. And this paper actually was the basis of many of the techniques that we eventually ended up implementing in Spark. So that's one technique. The other technique that I'm going to talk about today is improving Spark's in-memory representation. Now, there are not always things that you can actually fuse together in a single stage, either because we don't see any benefits of doing that, or it might just be too hard to just fuse this arbitrary code into a single stage. So while the whole-state code generation techniques works great for simple operators, projects, filters, aggregates, and many such cases, which, by the way, accounts for a large number of queries, we see that there are obviously cases in which you cannot just combine these operators into a single pipeline. An example of this might be just when your query is doing some kind of complicated I/O. So for example, if you're parsing CSV data or Parquet data, there might be some libraries that you might use to actually make sense of that data, and it might be just harder to fuse all of that logic into a single Spark query or a single stage. Another example of this is like if your query actually sends data across machines. So if your data is being transferred across machines, we cannot obviously have them in a single stage. Yet another example of this could be external integration. So for example, if my Spark code is just calling a Python library or an R library or maybe interacting with tensor frames, it's not easy to just fuse that code into a single Spark function or stage. So in order to get around this problem, we actually also worked on an in-memory columnar format for Spark. So before I go into the advantages of doing that, let me just tell you what it is. So in Spark, in the previous release of Spark, especially 1.6 and before, we had an in-memory row format in Spark. What this means is that if I have a data that looks like this, in which I have an integer column followed by a string column followed by a float column, an in-memory row format, as the name implies, store all of these columns or all of these data values consecutively. So you have an integer followed by a string followed by a float, and so on. The in-memory column format, on the other hand, is just the transpose of the row format. So you have all the rows for the integer columns together. You have all the string columns together, and then finally all the float columns together. Now, as many of you would recognize, this technique is already pretty common for on-disk formats like Parquet or ORC, and we'll see that the benefits that they get in the on-disk formats directly translate into an in-memory column format as well. So what are the benefits? First of all, these in-memory column formats are way more storage efficient. It's more dense, so you don't need padding between values, and everything just like packs very nicely. The data access is much more regular, which in turn is very efficient for the CPU. For example, if I have an integer column, we always access the data 4 bytes apart. So CPUs can actually optimize these access patterns. And in general, it's very easier to index into. For example, some of these column formats at the back could be implemented using a Java array or a native Java array. Second, it's much more compatible with many of the high-performance external systems, because many of these external systems are already columnar. So if I talk about NumPy, TensorFlow, or Parquet, since these formats already support an in-memory column format, when I'm trying to read a Parquet file, or maybe try to send data or read data from like these frameworks, we essentially can incur a zero serialization or copy cost to work with them. And finally, it's easier to extend these formats in order to add new functionality. For example, we can actually process dictionary encoded data at some point of time if we already have an in-memory column format in Spark. So just to kind of like give a sneak peek and talk about some of the changes that this in-memory column formats enable us, what I'm going to show you is how fast can we now read a Parquet data file if we have implemented an in-memory column format in Spark. So again, if you look at the second point, I have a Parquet file that has an in-memory column format that's stored on disk, and I'm trying to that has a columnar format, and I'm trying to read this file into Spark, which now has an in-memory column format, resulted in zero serialization and copy cost. So here are the numbers. On the top, I have the numbers from previous releases of Spark, which essentially could read Parquet file using the standard Parquet library into a row format at 11 million rows per second. At the bottom, I have the vectorized Parquet reader, which essentially is a reader that we created that essentially could read Parquet data into Spark's in-memory column format, and we almost get an order of magnitude more improvement. So it could read 90 million rows per second. So if you put it all together, so if you look at the numbers, you basically see that I talked about two things. First, in phase 1 of Spark, we worked on 3 things. One is better memory management. We laid the foundation of runtime code generation. And then we spent time and effort on cache-aware algorithms. In phase 2, which is Spark 2.0 plus and beyond, we worked on primarily on whole-state code generation and the support for in-memory column format. So both whole-state code generation and the vectorized Parquet reader that I showed you are enabled by default in Spark 2.0 and subsequent releases. So at this point, I would actually like to show you a small demo of how these things work in practice and how you could actually see a glaring difference between Spark 2.0 and 1.6 numbers. Can I switch the computers, please? So here I have a database notebook, and this is basically running a simple Spark 2.0 cluster. This essentially is a 60 gigabyte cluster. This has like a 30 gigabyte driver and a 30 gigabyte worker on which I'll be running these queries. So first of all, let me just define a simple benchmark function. So this essentially takes in a function as an argument. It does like what's the most simple benchmarking function would do. Just tags a start time, executes that function, tags an end time, and then prints that how long the function took. So the first question that I would like to ask is how much faster would be Spark 1.6 and 2.0 in summing up 1 billion numbers? So the whole state code generation flag is essentially set to false in Spark 1.6. So this is essentially disabling whole state code generation. And if I execute this query, So we see that it took around 9 seconds to run. Just a quick kind of like way of, if we look at the Spark UI, I mean, I can basically see that you can execute these queries, or you can actually see that these queries would be executed without whole state code generation. And if now I just turn the flag to true and execute the query, which would be equivalent to Spark 2.0, instead of 9 seconds, I see that this summing of integers has almost been faster by more than an order of magnitude, and it took less than or around half a second. Similarly, if we talk about joins, how fast can Spark join a 1 billion records? So here I have a table or a large range with 1 billion numbers, and then it's trying to join with a smaller range of 1,000 numbers. With whole state code generation equal to false, I have 1.6 here that's running. If memory serves right, it takes around 10 to 20 seconds to run, depending on the kind of query that you have. And then, in the meantime, maybe I can show you how it looks like in the Spark UI. So go to the SQL tab. This is the kind of the query that we have. So here's the query plan for just a simple join. So note that since it's running with whole state code generation disabled, like you see that all of these stages are actually like separate. The same query, now if I turn the whole state code generation to be true, and this is now equivalent to a Spark 2.0 query, and I run this query, you see that it basically finished almost like in 1 second. So again, like if you look at the Spark UI for this, go into the SQL tab, just click that query. If you see that most of these stages are now wrapped into a single whole stage generation. So all of these stages that are part of a single stage are now code-gen into a single function. And it's very easy to see like which stages are now fused and which stages are still like separate. This was the Spark UI. You can also like just basically see this same query. And if I just do an explain on this, it works very similarly. So note that I still have whole state code generation to be true. And I just type an explain. And you see that this is the physical plan for the query. The star that's basically preceding these operators indicate that this stage is part of the whole state code generation. So this is just a way of knowing that these stages are code-gen, whereas things like joins, which are spanning machine boundaries and things like that, are not. Can I have the slides back, please? OK. So just kind of like giving a brief overview of all the individual operators that we have. For filters, some group by sums, without group by sums, hash joins, and things like that, we almost see an order of more, like 5 to 30 times more improvements or speedups. In Spark 2.0, we also have a new radix sort implementation that's essentially 10 to 100 times faster. There are also some things that are not really optimized by whole state code generation. So code gen optimizes per iteration cost, but things like sort merge join, we still have shuffle, which is the real bottleneck. And finally, the Parquet decoding example that I showed you results in a 10 times speedup because of the vectorized Parquet reader. This is a similar graph that shows the TPCDS benchmarks and compares Spark 1.6 and 2.0 performance. So the lower bars are actually better. And we see that these per operator improvements pretty much scale or pretty much contribute to overall query improvements very nicely. So just one last slide on what's next. There are like a number of performance improvements that are coming in Spark 2.1, 2.2, and even beyond that I'm really excited about. So one thing I did not really talk about was the Catalyst Optimizer and how it actually is going to improve performance. One of the really cool things that is coming along, like in 2.1 and 2.2, is like a cost-based optimizer. Here we leverage table and column level statistics to optimize a number of queries, especially those with joins and aggregates. There is another effort around boosting Spark's performance on many core machines. And if you're more interested in knowing about this, I would recommend going to Shifan's talk today at around 3 p.m. in the research track, where he'll talk about in-memory and single-node shuffle. And finally, we are continuing to work on improving code quality of the generated code, and in general, integrating the in-memory column format better in Spark. And this is what is basically, this is what is keeping us busy for many of the future releases of Spark in terms of performance improvements. So that's what I had, and I'll be very happy to take any questions. I also have booth duty at the Database booth from 12 to 2 p.m. tomorrow, and very happy to take any questions around that time as well. Thank you.
Thank you, Samir. We only have